Thank you, everybody, for attending this talk, first of all. And thank you, RISC-V, for enabling youngsters so we can showcase our work in such a big conference. Thank you. My name is Umair Riaz, as he told, and I'm an RTL design engineer at Barcelona Supercomputing Center. I'm presenting today what we are doing, or what we have done so far in this project. We are coming up with something like innovative. What RISC-V is doing in breaking the monopoly, we are breaking the monopoly of a classical system, breaking cache. So I will explain later what we are doing. So this is the overview for the next 15 minutes so far. And I'll walk you through the motivation, what we have, why we are doing this, what we are doing. And I'll introduce you the memory engine we are coming up with. And to dig a bit deeper, I'll explain the microarchitecture and the types of requests we can handle with this memory engine. And later on, I'll try to explain the key components we have in the microarchitecture. And to wrap up the discussion, I'll have some result to show you guys. So we know that machine learning, graph-based application, they are like very common these days. And we all know that the performance of machine learning and graph-based applications, they are hampered by the inefficient use of memory bandwidth. That's what we are targeting. We are trying to come up with, we can have an efficient memory bandwidth use. So we want to reduce data movements, because moving data back and forth from memory tile to compute node or memory node to compute node is very energy consuming, or power. It takes a lot of power. What we are trying to do is to save parasitic movements. So there will be less parasitic movements between compute node and memory. That reduces NOC traffic as well. What we want to do is to have a better vector data processing, much more efficiently, to keep the semantics consistent without changing them into a cache line, and to improve, of course, memory-level parallelism. So this is what a classical system looks like. We have L2 cache, we have a compute node, and L2 cache talking to memory. So in this case, even though if you have a vector loads and store, they turn into cache line transfer. So now your vector requests are no more vector. The semantics have been changed, and they are now pretty much dependent on the cache structure as well. So if your vector is too large or sparse, and it doesn't fit in the cache, you're probably going to have some bad performance. So what we are trying to come up with is to put a memory engine next to memory, so we can deal those vector requests much more efficiently and locally. But what about the cache requests? They are like as before. They are like transparently by this memory engine. So to give you a bit of context where we are utilizing this memory engine, we have an ACME architecture. This is actually RISC-V-based architecture for sparse and dense workloads. So you can see we have a volatile. To give you the concept, this is kind of the core. Volatile core contains a scalar CPU and the corresponding VPU and some systolic arrays. And they have a memory tile in the pink color, as shown here. What I'm talking about is about the memory tile here. Our engine will be in that memory tile. So we know that VPU is very common for data-level parallelism. But we are trying to come up with the addition of this memory engine, we are exploiting memory-level parallelism as well as DPU, data-level parallelism. This is a microarchitecture of MEDEA. MEDEA is actually memory engine for decoupled execute access. So we have some key components like vector fragment sequencer, like Prefetcher, like MCPU, and interfaces. To keep it simple and conquer one by one, let's remove all the logic. We're left with this. So we have the interfaces. We have 4 interfaces. Now this engine is connecting with the external world with these interfaces. The first one is the CNOC. So what's on the other end? It's actually compute node. I told you we have a scalar core. We have the corresponding VPU. We get the request in this MEDEA through this CNOC. It's actually compute NOC, we call it. Second one is the VNOC, vector NOC. We have, on the other side, we have long vector register file to load or store data into it from memory. We have a memory crossbar where all the MEDEA tiles are connecting to each other. And the last one, we have a memory controller interface where we are connecting with HBM. We have a CPU inside this memory engine, and this interface will connect it to the memory for some memory-intensive operation that will be done locally. So after studying about or learning about the interfaces, it's good to know what kind of requests we can handle. So talking about that, some are like the canonical ones. First one is the cache miss read or cache miss write. Usually everywhere we can see. Those are handled transparently as before. And virtual to physical address translation, because we have TLB inside it as well, and a page table walk. The fun part is how to deal vector requests, vector load and vector store requests. So we are trying to deal these requests much more efficiently. And last, atomic memory operations. We are in a phase to support memory-intensive tasks that will be handled by the CPU inside this memory engine closer to memory, so we can save moving data back and forth. Coming back to the microarchitecture, after discussing the interfaces, now it's pretty much good to go to the key components. So the first one I'm going to talk about is the vector fragment sequencer. What a vector fragment sequencer will do or does is actually, if a vector is too large, now there's no notion of cache in it. So whenever you get a request of a vector load or a vector store, you break it into multiple fragments. You chop it down. But the question is, how many fragments? Who will dictate how many fragments we need for it, for a particular request? The memory crossbar data width and the bus length will decide it, because you're going to write it to memory or you're going to read it from memory. So you need multiple fragments, and each fragment will generate a corresponding memory transaction. So what you will end up having, all the data from memory, from all the fragments, you pack them locally, and you write it to LVRF as a dense vector. To dig a bit deeper, we know that RISC-V support 3 types of addressing mode: unistride, strided, or indexed. Our focus is more toward strided and indexed mode. Why? Because they are like for sparse memory accesses. And there's very key phenomena here happening. If we fragment our request, in case of a very sparse vector, we might end up having a fragment, might end up having a single vector element after getting from memory. What we are doing, we are in this memory engine, MEDEA, we are taking data from all the fragments, packing them locally, and writing to a vector register file or long vector register file as a dense vector. What will eventually we will have is less parasitic data movements. So you are moving less parasitic data from memory all the way to compute node. Especially in case of stride, you need to put off some byte lanes. And this memory engine will do inside locally and make a dense vector write to vector register file. So consequently, we can save energy, and the good thing, we can save NOC traffic as well. Another component is Prefetcher. What a Prefetcher does is actually, we know application is demanding some vector length to perform operation on application vector length. But our long vector register file is a physical register file, which means we have some physical constraints. So the GVL, which is granted vector length, that is actually constrained by the physical limits of the LVRF. But Prefetcher inside this MEDEA memory engine knows both. What we will do, whenever the request arrives, we work on GVL. This memory engine will work on GVL. But it knows application vector length as well. What it will do, it will prefetch, but non-speculatively. So knowing that, keeping the fact in mind that the request will eventually arrive. So I repeat, this is non-speculative prefetch. We are prefetching things from memory. We know what application is demanding. We know on which application we are working on. So we know both. So before the next request will come up, eventually we get the data earlier than that. So this can save time. Whenever the request will arrive, it will process much more quickly. Another key component we have in this memory engine is memory CPU. The work is still going on. This work is in progress. This is kind of a scalar processor. We need just few architectural extension, no more than that. It's tightly coupled with memory and having a low latency interface to the memory controller. Why we need it? What we want from it is actually to do memory-intensive operations closer to memory, like memcopy or spin lock. We can have a memory CPU inside this memory engine to perform those, which also reduces taking data along the way. And executing function locally will eventually get performance, energy, and less knock traffic, because you are doing much more closer to memory, this memory engine. So as a token of appreciation, we have some result to show you. This is sparse matrix benchmark. And look at the blue curve. Without this memory engine, if on the x-axis we have number of elements for x to be reused, and if that number is too high, if the x factor is too large, and the number of elements to be reused is too large, and if it doesn't fit in the cache, what will eventually you get is frequent eviction. So look at the blue curve going up. Whereas with the introduction of this memory engine in the system, you can have a better performance, much better performance, because there is no notion of eviction and such kind of things. So look at the red curve. This is pretty much what we have done so far, and we are still working on it, and probably in the next summit we have some more result to show you guys. Thank you. Questions? By the way, I'm also presenting it in the poster session. So if you guys want to have an in-depth discussion, we can have there as well. Thank you.
Okay. Let's thank the speaker. Yes, so thanks, Umair. There's a question, sorry. Please go. No?
Okay.
Yeah. Sorry.
Sure.
May I ask, how do you deal with cache coherence problem?
Sorry?
Cache coherence.
Yeah. So our vector requests are like non-cacheable.
Vector requests are uncacheable, right?
Non-cacheable. Vector requests are non-cacheable.
Now, how about scalar requests in your?
Yeah, we have coherence at the L2 level, not at the L3 level. So L3 we have inside this memory engine is kind of consider it as a row buffer for memory.
So how many cores do you have in your SoC?
How many?
Cores.
We have 8 VASTile cores, and in every VASTile cores.
So 8 L1, right?
Sorry?
8 L1 caches.
Yeah.
So
L2 is shared, and the coherence point is L2.
So all the vector requests are sent directly from courses to L2 cache, right?
No. To this memory engine.
To memory engine?
Yes.
Okay, thank you for telling me.
Yeah.
So have you ever considered memory consistency model?
Memory
consistency?
I don't think so.
So do you induce out of order or non-blocking cache?
No, not yet. We are using in order currently.
In order.
So
your core execution is in order. Then how about do you adopt non-blocking cache design in your cache design?
So you are concerned, I think, with the cache coherence about scalar and vector. Vector requests.
For vector.
Yeah.
Do you adopt a vector
Yeah, I'm saying that-
non-blocking? Do you adapt a non-blocking design in your vector design?
No, but actually,
Sorry for that. Sorry to break the discussion. Probably it's lunchtime and all
Okay,
of us are
okay.
very hungry.
we can have this discussion on the board.
Yeah,
Okay,
I
okay.
encourage you to.
Thank you for giving me the chance.
Research him in
See
the
you there.
poster session. So with that, we conclude the session. Now we have lunch. Recall that at 1 the demos start again on the demo theater. So feel free to join that at 1 p.m. Thanks for attending the session and enjoy your lunch.